In this lecture on dry etching, we are going to look at etch chemistry, in particular etch chemistry of silicon and silicon dioxide. So these two materials are predominantly used in many applications, including microelectronics, MEMS, NEMS, photonics, and various other sensors as well. So let us look at what is the chemistry that is required to etch these two materials, silicon and silicon dioxide, and how are we going to achieve selectivity as well. So as I mentioned, we are going to look at the chemistry between silicon and silicon dioxide etch process. Basically, we are going to look at the gas chemistry. So what kind of precursor gases that we are going to use and how we tune the chemistry. Selectivity. Right. If you want to etch one material preferentially while the other material is exposed, how do we differentiate the etch rate between the materials? Loading effect is a cause of various factors in design and also the process. So let us understand what the loading effect is, and then finally we'll also look at a special type of etch which is called deep reactive ion etching, which is used in modern day integration. So primarily silicon and silicon dioxide etch chemistries uses halides, right? So it could be chlorine, bromine or fluorine, right? So iodine also comes under the category of halide, but it is very hard to control halide. The pressure is very hard to control, so it's not used in etching. So we primarily use chlorine, bromine and fluorine as gases for etching, and we use it in combination with carbon as etch gas, because you don't want to use, you either use chlorine as a separate gas or you do CCl4, right? So when you do CCl4, you get a large number of chlorine rather than Cl2. Right, so that is the primary idea. A stable gas that should carry most number of reactive species. And in addition to the reactive gases, we also add some reactive and also noble gases for dilution and also enabling the reaction. So a few of them are argon, oxygen, helium, hydrogen and nitrogen, or few to name. So this helps us in engineering the plasma and also engineering the chemistry. We will look at shortly how these chemistries work. First of all, let's look at silicon, right? So silicon etch is primarily done through tetrafluoromethane here, right? So that supplies fluorine. So fluorine is the gas that would react with silicon to make a volatile product, in this case SiF4, right. So as we already discussed earlier, so argon, the diluting gas or the noble gas, is primarily used to supply large number of electrons, which helps in dissociating the etch gas to create radicals. Right. So one of the downside in this reaction is the following. So you want to create a large number of fluorine, but if you look at CF3, which is a radical, so they can combine and make hexafluoroethane here, right. So now you are losing. So this compound is stable, right. So you don't want this reverse reaction. So how do you stop this reverse reaction and enable fluorine generation, right. So you want to reduce fluorine loss here, right, and sustain chemically reactive species, in this case fluorine, in the plasma. One way of doing that is by adding oxygen, right. So when you add oxygen, so it reacts with all the radicals that you have, and then finally produced carbon dioxide gas, and then you will have fluorine radicals coming out, right, because carbon likes to be with oxygen, right. So you always generate volatile product, in this case gas, carbon dioxide gas, which can be easily stable gas, which can be easily extracted, while fluorine can be used for a reaction. So this is how we add this additive gases to work out a chemistry with which you can increase the reactive species, in this case fluorine. So addition of oxygen, right, to CF4 helps you in increasing your fluorine radicals, and this also helps you in achieving higher H rates, right. So when you don't add oxygen, your H rate is going to be low. So this is what done a long time ago, understanding how oxygen percentage helps in H rate, right, of silicon. So as you can see here, the H rate increases, right, and this one is the H rate, and this is actually the emission spectra. This is the line intensity. So this is the plasma diagnostics. We discussed about excitation, right. So in this case, this particular emission is coming from silicon edge, right. So when you look at this particular emission from the plasma, we would know the silicon is being etched. So the etch rate actually increases to a certain oxygen percentage, and then it starts to decrease. So let's look at the left hand part, where adding more oxygen into the plasma helps you in increasing the H rate. On the other hand, too much of oxygen actually does the reverse, so it reduces the H rate. The reason for this is you create oxygen radicals which could form, oxide surface on silicon, which will prevent chemical reaction, and also you are diluting your CF4, right, too much. So the combination of dilution and also formation of oxide on the surface of silicon, right, so you have oxygen radicals that can come in, and then it can form a very thin layer of silicon dioxide, right, which will prevent your fluorine, right, from reacting onto the reaching silicon, right. So there is no reaction here, so or the reaction rate is very less. So this is how you achieve reduced reaction, right. But you always want to increase the reaction rate, so you want to operate, below this optimal oxygen percentage, so that your H rates can be higher. Not only for H rates, you can also use oxygen to tune the sidewall angle, right. So when you add oxygen, it always creates some sort of silicon oxycarbide type, polymers that settles on the sidewall. So these polymers are generated and then go and settle on the sidewall. So when you reduce the flow of oxygen, right, when you reduce the flow, you can see here you are getting an anisotropic edge. So you can almost see a 90-degree angle here, right. The reason why this is 90 degrees is because the sidewall coating, right, is slowly reducing. The thickness of sidewall coating is slowly reducing, but in the last case you have started doing isotropic edge. So there is no sidewall coating at all, right. So you start attacking the sidewall here of silicon, right. So by adjusting the flow of oxygen, one could actually tune the sidewall angle. This is again, the chemistry driven profile improvement. So let's look at silicon dioxide chemistry. Fluorine also etches silicon dioxide, right. It attacks both silicon and also silicon dioxide. Etch rates could be slightly different, but it attacks. But what you want to do is to achieve selectivity. So if I am etching silicon dioxide, I only want to etch silicon dioxide while silicon is unaffected. Similarly, if I am etching silicon, I don't want the chemistry to attack silicon dioxide. This becomes particularly interesting, right, when you have material A and material B, which both of the materials are exposed, let's assume, right. But then you want to etch only material A, not material B, which is also exposed. So just to give you an example, so if I take a gate dielectric particularly, so this is silicon dioxide, which is gate, and then let's say we have silicon underneath, and this is also polysilicon, right. And there is mask here. So I am etching this silicon from here, but then when I hit this silicon dioxide, my reaction should stop, right? I don't want to etch this oxide. If I etch this oxide, then I'm going to damage my device, right? So I should stop when I hit silicon dioxide. So this is what selectivity is all about. When I'm using polysilicon etch process, I should only etch polysilicon. When I expose silicon dioxide, the reaction should stop. That means my chemistry should not etch silicon dioxide. So we used oxygen in case of silicon etch to increase the etch rate, right? In this case, we had hydrogen to the plasma, right? So CF4 plus H2, right, is what we had. So interestingly, when you have 0 H2, right, so when there is no hydrogen added to the plasma, you look at the selectivity between silicon and silicon dioxide is very small, right? So they etch, within 5-10 nanometer per minute difference only, right? But then when you start adding hydrogen, then you slowly see your polysilicon etch rate reduces tremendously, while your silicon etch rate only changes marginal. But again, the interesting thing is your resist, right? Your resist etch rate dramatically reduces. This is again an interesting thing to notice, because you are improving your selectivity with respect to resist as well, right? So this is how you adding hydrogen, which is an inert gas, right, is helping you to improve your selectivity between silicon dioxide and polysilicon, and also photoresist, right? So the right side graph is the same graph, but we are only looking at the selectivity, right? Selectivity with respect to polysilicon and silicon dioxide etch rates. So adding any kind of additive inert gas can also help you in achieving selectivity. So let's look at what is actually happening, right? So we did Auger spectroscopy. So this was again to understand whatever happened in this experiment long time ago. People are trying to understand what is the driving mechanism through which we are getting this selectivity. So what they did was they took a clean silicon wafer, right, and then they did Auger spectroscopy on this, and then observe really a clean signal. They were only able to observe only silicon, right, and little amount of argon which was present in the chamber, right. But then when the surface is bombarded with CF3, then after exposing it for a while, and then after that when we observe the surface had lot of carbon and little bit of fluorine, understandably, because but we had lot of carbon deposits in there. So when you have carbon deposits, then the reaction chemistry is preventing, right, this radicals to reach the silicon layer by protecting the layer using this carbon blocking layer, right. And this is what you see when you look at various CF3 plus concentration irradiated on oxidized silicon and also on just pure silicon. So the signal, the carbon signal on pure silicon kept on increasing, while on oxidized silicon you saw a marginal change in the surface property. The main reason for this is the chemistry that happens between oxide and CF3, right. So this is what actually is happening there. So when the carbon blocking layer is formed on silicon, so you create the gas, and then you still have the solid here. So basically there is no reaction, right. So the radicals come onto the silicon surface and you don't see any reaction at all. But then when you have the same radical exposed to silicon dioxide, you create SiF4, which is a gas, and CO, which is a gas. So here you see etching. So by creating a blocking layer, you are able to stop your radicals reaching silicon, and this is how you can create selectivity. And the other way to create selectivity is by creating non-volatile product. So let's say I have material A and material B, right? And then I come in with H gas E, let's say. So E reacts with A to produce, let's say, EA. And similarly, E reacts with B to create EB, let's say, right? So in this case, if I want to have high selectivity, I should create EA as a volatile product, and then EB should be a solid. So if this is the case, then all the reactions leading to EB will not generate any H product, so they will just sit on the surface. And this is how you can create volatile, non-volatile product driven selectivity. And the other way to do that is endothermic reaction, right? So when you create endothermic reactions, right, when the reaction path is towards endothermic, then you can also arrest this reaction and then create selectivity. And the other interesting way to create this is by using low ion bombardment. So for instance, if you take a CF, again a CF4 based plasma, right, and in this case both silicon dioxide and silicon will etch, right, but the only difference is there is a slight lag in the etch rate. But then when you start bombarding, right, when you increase the ion energy, so when you increase the ion energy, your silicon dioxide etch rate increases. So in the presence of ion bombardment, your oxide etch rate would increase, right? And you need to find the right ion energy that allows you to maintain the H differential, right? And if you keep on increasing the ion energy, your silicon dioxide etch rate can be beyond silicon etch rate. The reason for that is you start doing physical etch, okay, as opposed to chemical etch. So by adjusting the ion energy, one can achieve selectivity. So another important thing to note in dry etching is loading effect. So loading effect is nothing but a non-uniform etch rate, right? So as a function of distance, right, where as a function of location within the sample that you are doing or within the wafer, right? So if the etch rate is non-uniform, we call this as a etch non-uniformity, or there is a etch loading. So this is primarily based on pattern density coming from the design and the exposure. The other reason could be non-uniformity in plasma as well. So we saw that if you keep the wafer and then you create a plasma like this, right? So the ion energy, right, and the radical concentration need not be uniform across the wafer, right? So one need to design the chamber in such a way that you have very good uniformity of ion energy and the flux. So if you don't have it, you get non-uniform etch rates. The other reason is pattern dependent. This is coming from the wafer itself. So you can have local loading or global loading. Global loading is happening throughout the wafer, right? So if you have a 200 millimeter wafer, so the variation across this is called global loading. Local loading is within the device or few tens of micrometer distance, right? If the etch rates are changing, then we call it as local loading. So here a schematic is shown to show how the etch species density varies. If you have a dense part here, right, this is dense and this is isolated. So in isolated region, you have a large number of H species, because whatever radicals come in, you have all of them available to migrate for the reaction. But in this case, you have open areas where these radicals could be consumed, right? So that is the reason the species density is lower compared to a isolated line, and at the edges you see a differential, right? So this is where you see the transition from no patterns at all and suddenly you have pattern. So all the radicals that are coming down here, they can migrate and then help in the etching, right, of this first tooth, which actually is a micro loading effect, right? So that is what we observe here, right? So there are two type of local loading, right? One is really a micro loading, where you have an opening, right? So ideally this should have been like this, right? So you have a metal, and then we had something like this, right? So this is metal, and then you want to etch, and then you land on metal, okay? But what happened here is there was a misalignment. So the misalignment has given, a small opening that exposed it to silicon. So now once you hit the metal, because of this notch that you see here, you have all the radicals here that can go and react with this silicon. So here the etch rate is going to be very high because there is no reaction happening on this metal. All the radicals can migrate to this silicon opening and then etch it. So this can be accelerated etch called microloading. The other effect is aspect ratio dependent etch, right? This is aspect ratio is nothing but the ratio between width to height, right? So a smaller opening and a large opening. So a smaller opening with a deep is called higher aspect ratio compared to a large opening. On the right side you will see the actual cross section image, right, of the effect of this aspect ratio dependent etch. A large opening etches deeper, right, while a narrow opening it only etches shallow, right? So there is a lag in the edge, right? So the edge depth difference is coming from the aspect ratio. So the reason for this is, the getting in all the etchants and also getting all the products out. When the opening is large, the impedance for the etchants to go in and come out is very less. So you can have a free flow of etchants and byproducts. But when you reduce the width, you have a large impedance for the etchants to move in and also come out, right? So this differential in movement, right, the diffusion of etchants and byproducts creates this edge lag. Right, on the right side you can see the critical dimension. Let's say this is the width. As you increase the width, right, as you increase the trench width, you increase the etch depth, right? So this is indicating that your etch rate is much higher in aspect ratios, lower aspect ratios, right? And the next thing is deep reactive ion etching, right? So whatever we discussed so far talks about just reactive ion etching. Deep meaning you want to etch tens of microns, let's say hundreds of microns. So this was a process that was developed by Bosch. It's still called Bosch process, where you want to have highly anisotropic etch, right, to etch through silicon wafers. For example, a silicon wafer can be anywhere between 500 to 750 micrometer. So you want to etch through this whole layer. Right, so you want to remove silicon throughout this layer. How do we do that? Because we already saw if the aspect ratios are high, it is very hard to get the etchants in and out, right, because of the directionality issue. And this Bosch process or deep reactive ion etching was really used to remove the substrates to enable MEMS processing. MEMS process uses a lot of released structure. You want to have free hanging features where you have thicker layer of silicon that is being released, and this is free to move, right? So those are all the structures that uses DRIE. And the main idea here is the DRIE process uses isotropic and anisotropic, a combination of this process, right? And if you are going to use highly isotropic process, then you worry about lateral etching, right? So isotropic process means lateral etch. So how do we prevent this lateral etch is the specialty of DRIE. As I mentioned, we use this for MEMS application, right, and also for a lot of this power devices where you remove the silicon substrates to have good contact with the device for effective heat generation, and then you have through silicon vias, right, to connect two different dies. For instance, I have one die, right, this is die 1 and then this is die 2. So how, if I want to connect these two, so you can make deep trenches, right, and then by doing that we will be able to connect all of this electrically, right? This is what is used in present day memory chips, right? With high density memory chips, we use through silicon via, right, for 3D integration. So let's look at how this process works, right? We start with photoresist as a mask, right, and then or hard mask if you want, right? So it depends on how deep you want to etch. If you want to go really through the wafer, you can use a hard mask, which can be oxide, nitride, or alumina. In this case, you start with SF6 plasma, where you supply fluorine in order to generate SiF4, right? And then you use C4F8, right? So now you are using alternate plasma. So in the first cycle, we use SF6 to etch, and in the next cycle you put a passivating layer. So you create lot of carbon deposits, and then you cover it, right? So it covers the sidewall. This is very important to see. And then in the next cycle you again go to etch now. So now you are attacking the vertical, the isotropic edge, while you are protecting the sidewalls, and you repeat this cycle, right? So cycle 1, cycle 2, cycle 1, cycle 2, you keep on repeating this SF6 and C4F8, and then you will get a pattern like this. And what you see on the right side is the SEM image of a really deep pattern, in this case about 40 micron pattern, right? And if you zoom in, you will see how this coating and isotropic etch is happening, right? So you will see a pattern like this, right? This is called the scallops. So as I mentioned earlier, there is isotropic etch, and then the protection of the sidewalls, right? And then you keep on moving vertically in, and this is how you make this. So you can clearly see the isotropic nature here, yet you dig deeper, right? So you can go deeper in vertical, and this creates scallops, right? So this is each cycle. Each cycle creates this, but sometimes these are all undesirable. So you may want to smoothen it out, right? So you can smoothen it out by using isotropic plasma. You can put it through isotropic plasma, and you can see here, about 1 micron reduction in the plasma in the scallops, and even in the more optimized case, you don't see any scallops at all. It's completely gone. It's a very smooth etch process, right? So by using a combination of isotropic and anisotropic, we were able to etch very deep trenches without having this isotropic artifact. Okay, so with this we come to an end of this dry etching lecture series. So where we discussed in detail about what are all the required plasma processes, and the chemistry required, the tool requirement, and how do we use different sort of additive gases in order to optimize the etch process, and also by using additive gases to change the profile, right? And also some of these undesirable features that you get because of loading, right? So loading is primarily from the density, and once we understand the density distribution, we should be able to address the non-uniformity in etch due to loading as well. So with this, I hope you all got a very good understanding of dry etching process.